Hi, it's great to be part of this after-lunch session of HPDC. I was not able to be here in person because of visa issues. I hope this video makes up for it. In case there are any questions, feel free to ask them at the end of this presentation. This work is on identifying communities on graphs that evolve with time using a modified version of Leiden algorithm, a heuristic-based approach. I'm Subhajit. I work as an assistant professor in the Department of Computer Science and Engineering at SRM University, AP, India. Given a graph, which is a set of vertices and interconnecting edges, commute detection tries to identify the inherent structure in this graph, which implies the function performed by this. Strongly connected regions, the idea is strongly connected regions in this graph perform a specific function, and then these regions interact among themselves to perform the overall function, such as in a brain network. The number and size distribution of these communities is not known beforehand. And this is in contrast to classification, where we have a fixed set of classes. Given a community assignment, the quality of the community assignment uh, can be identified using a modularity metric, which ranges from -0.5 to 1, which where higher is better. This is the equation for it. Optimizing modularity is an NP-hard problem, therefore heuristic-based methods are used. The Leiden algorithm is one such heuristic-based method. It consists of multiple passes where each pass identifies communities at a particular level. Then these communities are grouped together into larger communities and then larger communities until it converges. Each pass has three phases: local moving, refinement, and aggregation. Uh, Initially, each node is its own community. In local moving, each node selects the best possible community to move to. Then uh, each such identified community is improved and internal disconnections are removed using refinement phase. The refined communities are then aggregated or grouped together into uh, supernodes. These supernodes are then processed in the same way as before for multiple passes. Now that is the static Leiden algorithm. To apply it on dynamic graphs, there are three possible approaches. Naive dynamic, where we simply take the previous community labels and apply the Leiden algorithm, or we select a subset of vertices to process and only perform the algorithm on these subset of vertices, that is delta skinning and dynamic routing. That's slightly different. The issue with existing methods is, first of all, running the static algorithm is expensive. Dynamic algorithms can help here. Next, the stability is important. The tracking of communities is important. But the refinement phase in the later algorithm renumbers communities, which prevents tracking. We cannot remove this refinement phase. It is essential for the quality guarantees provided by the later algorithm. Existing implementations either have no stability and poor performance, or they require processing the entire graph across all snapshots in time. Our methods, our method only requires the current snapshot. We have three steps or approaches. So the first step is improving stability. Since the renumbering in the refinement phase requires or prevents tracking, we use an overlap-based tracking method where the community, the idea is for each old community, we find the most overlapping current community. And for this for each current community, we find the most overlapping old community. If these are the same, then the current community is mapped to the old community. For this overlap-based tracking, we use the Boyer-Moore majority vote algorithm uh, in, in order to achieve good performance, and we use atomics wherever necessary. If the community overlap does not match in both cases, like from old to current and current to old, such communities are assigned new unique IDs using a thread safe method. This figure shows the process. For A is an old community, C is a new community. A has the highest overlap with C. However, C seems to have the highest overlap with old community B. Therefore, C is not specifically mapped to A. C is assigned a new unique ID. If, however, C would have been having highest overlap with A, C would have been mapped to A. The other step is minimizing communities to refine. The problem with refinement is it is expensive, and a refined community needs to be hierarchically merged. Therefore, what we do is we aggregate the edge updates until the total edge weight of the updates is greater than refinement tolerance. For example, if we have a small edge update, we do not refine community A, another update comes in and the total update exceeds refinement tolerance, then we finally perform the refinement phase. And this is repeated for edge deletions and insertions. But since we are doing this selective refinement, we need to ensure these communities which are not refined, we need to ensure that they do not have any internally disconnected communities. So we have a BFS based parallel algorithm which splits such unrefined communities. But again, we can do this selectively. Uh, if the community is unrefined, but there is no vertex migration or there is no intra-community edge deletion, such a community cannot break, and therefore we skip splitting such communities. So this selective splitting is done only in these two cases, where there is a vertex migration or intra-community edge deletion. So these are the three steps. We evaluate our approach. Our approach is applied to naive dynamic, dynamic frontier, and delta scaling, and we compare it with the static Leiden algorithm on this data set, which has up to 214 million vertices and 3.8 billion edges, web graphs, social networks, row networks, and protein KML graphs. These are static graphs. We generate random batch update consisting of 80% edge insertions, 20% deletions, and this random batch update size of this update ranges from 10 per minus 7 the number of edges in the graph or zero point 0.1 the number of edges in the graph. Basically a fraction of the edges in the original graph. As the size of the batch update increases in the x-axis, the runtime of the static algorithm shown in blue increases. Same is the case with the dynamic algorithm, but the dynamic frontier-based approach has the best performance and is faster than the static algorithm. In terms of modularity, all algorithms roughly achieve the same modularity. The modularity drops as with increasing batch size because the community structure is disrupted because of the random batch update. So this shows that our algorithms achieve the same performance in terms of quality, community quality as the static algorithm. Here we observe the affected vertices identified by delta screening and dynamic frontier, the number of or the fraction of committees that are marked to be split, and the fraction of committees that are marked to be refined. And here we observe that dynamic frontier has a smaller set of identified affected vertices and small set of marked committees to be split, but similar in the set of committees to be refined. We increase the number of threads in each implementation from one thread to to 64 threads. The system has 64 cores, and we observe this static algorithm has the highest scaling because dynamic algorithms have reduced work in this case to be performed. As a conclusion, um, we introduced three techniques for commit tracking and improving the performance of dynamic Leiden. Future work could possibly explore improving the performance, further improving the stability, or using other quality metrics for optimization. Thanks a lot for listening.